The 2 by 2 and 3 by 3 determinants can be interpreted as being an area and a volume. In particular, let's say we have a parallelogram determined by vectors AB and BC, and this is the origin. So the area of this parallelogram turns out to be determinant of the matrix whose components are AB. I'm sorry, this should be CD. Those 2 points don't necessarily have anything to do with each other. It should be that in absolute values in case it turns out to be negative. And we could put the CD point first and the AB point afterward. It doesn't matter if we're going to take absolute values, because then we just get the absolute value of AD minus BC, or equivalent to the absolute value of CB minus AD. Those are both the same since we're taking absolute values. Now the area of the shape called a parallelepiped, so it's determined by 3 vectors in 3 spaces. So we'll have 2 vectors and then something else up here. And we'll have a 3-dimensional solid, which maybe you can picture. I'm not going to try and draw it, but the area of the parallelepiped, which has an E after parallel as opposed to parallelogram, which has an O after the parallel. So the area, the volume of the parallelepiped, because this is a 3-dimensional figure, determined by points A1, A2, A3, B1, B2, B3, C1, C2, C3. Is probably what you would guess. It's the determinants of the matrix we get by putting these points together in absolute values. And we can put these 3 points in there in any order. I'll put them in the same order I draw them here. And for the figure, which I tried to make with magic markers in the air in this picture, I'll refer you to the book, page 205. For the picture. The end.